So this is the second part of this set of lectures on the Ax-Schanuel theorem for the J function. So today I will present the linear differential equation associated to the J function and a good set of equations we have to use to present this linear differential equation in order to apply differential Galois theory in the third lecture. So, as I already said you last time, the function J, this function here, can be defined as a special solution of a non-linear differential equation. I will write it again here. You take the logarithmic derivative of derivative, you take the derivative of that, and you take out the half of the square. Then adding our special rational function I gave last time, evaluated on J prime square, this is 0. So this particular operator that appears here has very nice property. It is called the Schwarzian derivative. The Schwarzian derivative without this is this operator that I will denote by S. There are many different notations for this operator. It's a function. Here I will use y for a differential unknown, so an unknown that you can derive with respect to t. Our variable here is t. It is this one here. So usually you will not find this form for the Schwarzian, but you will apply the derivative and you can find this in textbook. And some notation here will show the variable you're using to take the derivative. So for instance, you can also have this kind of notation, y and t, which is I think it is Cayley notation. So this operator, which is central in this equation, has two very nice properties that will give some nice property for the solution set here. So the two nice properties we get are the following. The first one is a compatibility with the composition. So if you compute the Schwarzian derivative of a composition of function, then you get the Schwarzian of f evaluated in g times the derivative of g squared plus the Schwarzian of g. Yeah, so you can prove this directly by computing that. And the second nice property is that you know the zero set of this operator. So if a function annihilates the Schwarzian derivative, then, and this is the only case, so this is 0 if and only if you can write f of t as an homography, fractional linear map, a t plus b over ct plus d for some f. So let's say a, b, c, d, which is a matrix. You can, because you can multiply all the numbers here, A, B, C, D, by common complex number. This you can see in SL2 or C, and I will write, for me I will write, instead of this, F is in P, SL2 of C, as I said last time. So these two properties, you can prove them directly, okay? This is direct computation, and this is just a matter of solving a differential equation, and you see the differential equation here. You say that this, you call it, let's say, Z, and you have Z here. So you have Z prime minus 1/2 of Z squared equals 0. So it is an autonomous equation. You can solve it explicitly, and then you have just to solve y second equal to zy prime. And you find this shape for the solution. And as you have 3 constants here, okay, 4 minus 1 for the determinant, then you have all the solutions. Let's say, to be precise, all the non-constant solution, as I will imply f prime not 0 in order to put it in this equation. So here, everything I'm looking at is always solution with non-zero first derivative. So this property will imply 2 nice behavior of our set of solution of this equation. So there is a group, which is this one, acting on the solution. So PSL acts on solutions. So it means that if you take a solution, for instance your function j, if j of t is a solution of your equation E, then j of at plus b over ct plus d is another solution. Is also a solution. So it acts in a, let's say, the set of solution is a principal homogeneous space, in the sense that if you take 2 solutions, you have always one homography, one element f to go from a solution to another one. So let G1 and G2 be 2 solutions, and J2 be 2 solutions of E, then you will find an element in PSL2 of C such that this is obtained from this one using this formula. J1 is J2 composed with F. So the group is coming here, and we will use, in a way, we'll use this group action to linearize our equation. So the equation we are interested in, this E, can be seen as a what I call last time a Pfaff system. Meaning a system of one form on an algebraic variety whose integral curves are trajectories are parameterized by trajectories whose trajectories are parameterized by the j function. So here is our space. We start by y, which is just the space where j is taking its value, so it's c minus these 2 points. And then the phase space is c plus y plus c star for C with some coordinate that I will call T, Y, Y1, Y2. And the path system is this, so you have so dy minus y1 dt, dy2 minus dy1 minus y2 dt, and dy2 minus, and here you put what you want in order to have the interpretation that this is a derivative of y, this is a second derivative, this is a third derivative, so it must satisfy something here, and this something can be written like this, 3/2 y2 square over y1 minus r of y, y1 third dt. And so your equation can be written in this form. So you're looking at leaves. Of this Pfaffian system, which means analytic submanifold that are tangent to this form. Okay, the tangent space of this analytic submanifold L is included in the Zerocus of this one. I will write this. So if you write I for the injection, the immersion of this into your phase space, and you write this system as a set of form, I will call it T omega 1 for the first one, omega 2, and omega 3 for the last one, then you're looking at analytic immersed connected submanifold, which are maximal and such that the pullback of the form are 0. Meaning that at each point here in the image, the tangent is in the kernel of this. Okay, and these are parameterized. Parameterized by T is sent to, and I will use this notation, y of t, y prime of t. Maybe the first one is t itself, and y second of t, with this function here, must be a solution of the equation E. The solution y, the solution of this equation. Yeah, so this equation, then this parameterized curve will define you a map from a germ of, from a disk to this set that is tangent to this form here. Okay, and we are not directly, so we know many things on this analytic submanifold, and what we want to do is to know something about the product of these leaves in the product of this file space. So, as I said, this equation in fact is linear, and I will show you why it is linear. And then, among all the equations, among all the path system that exist to present a linear equation, linear differential equation, there are one that are better than the others. This is what we call principal form of the equation. Okay, I will. We will go to the linear system in 3 steps. So there will be 3 columns here. So the first, on the first line of the column, I will give the equation. So the equation here we are interested here is this Schwarzschild of y plus r of y prime squared equals 0, and it lives on the phase space. So the space where this equation reduced to order system of order 1 equation. This is c plus y plus c star plus c with coordinate t, y, y1, y2. Okay. And then a natural equation that is associated to this one is this equation here. That is the Schwarzschild of t, which is equal to r of y. But be careful, here we change the derivative, meaning that now we take the derivative of t with respect to y, meaning that the phase space is now c cross y cross c, c star c, with coordinate y, t, t1, and t2. And the last equation that we are using is the one we want. Is this equation, which is linear second order. The second derivative of u is 1/2 r of y times u. Okay. And the phase space now, in order to get this equation here, you know that the linear second order equation has a companion form which is a rank 2 order 1 linear equation. And in order to get all the information, I will write it in the fundamental form. Fundamental form of the equation. What does it mean? It means that we are working on, and the phase space is this one. Yes, with coordinate y and big U, which is the matrix of coordinate U1, 1, U2, 1, U1, 2, U2, 2 here, with determinant equal to 1. And the P here means that for us this matrix and minus this matrix are equal. Is identified with minus U. Okay, so what are the relations between these two? At the level of solution, here it's so easy, so not so easy, but it's consequence of this nice formula about the Schwarzschild derivative, so that if you take one solution, then this is an analytic, local analytic function of the variable t. Then you can inverse it, because the derivative is always non-zero, as I said. And the inverse satisfies this one. This is solution. And you can reverse everything. Yes, it is just the first nice formula for the Schwarzian derivative. Then here, on this side, the formula is a little bit different. And so here, you take u1 of y and u2 of y, independent, a basis of solution. The basis of solution here will give you one solution in the fundamental form. And the relation between the two, it's easier to go this way, is to write t of y, which is u, let's say if I take 1 or 2, 1 of y divided by u1 of y divided by u2 of y. And then you get a solution of this one. So these are classical facts, and here you see the group action, because you choose another basis of solution, then you have a matrix that change your basis, and it acts on the quotient by fractional linear map. So these are the phase spaces. Now the equation that I present as tap system, as I said. That's okay. So I define this equation as one form. So here we've already seen that. And dy2 minus something here that was written in this part of the blackboard. This equation here on this phase space has quite the same formulation. It's the t1 here. I said minus equals 0. dt1 minus t2 dy is equal to 0, and dt2 minus 3/2 of t2 square over t1 minus r of y t1 is equal to 0. Okay, these are the set of equations. And on the other side, you have to write this equation in the fundamental form, so meaning d of your matrix here it's 1 here, 2, 2, 2 minus d, I will erase this now, dy 0, 1/2 of r of y, dy 0 times u1 1, u2 1, u1 2, and u2 equals 0. So you have the matrix form of this equation. So you see 1, 2. If you write this as a matrix of form, you have the form here, the form here, another one here, and the last one here. But you can see that in fact this one is minus the first one. Yeah, as the determinant is 0. Oh, it's not exactly true. Okay, we want this, and I do not have that up to now. So you have 4 differential forms that are not linearly independent. As you have this relation here, and you can take the derivative of this relation, you will have the trace of u minus 1 du, which will be 0, and this one is 0 also. So the form obtained in this place and this place are not completely independent. But it is not exactly what I wrote here, and what I just erased is our goal, obtain something like this. Okay, we have this form on this big space here. So what you can see is that all these are the same. So you have the point that is missing is the group action. Or let's say directly PSL2 C action. So I take matrix A, B, C, D with determinant 1 and up to multiplication by -1 if I need, and I have the inverse of this matrix. Which is just dA minus B minus B minus C. Okay, and then this matrix act here using the inverse matrix here. So I keep this in mind, and now the action here is the following. You have T, Y, Y1, Y2 that are sent to, so it's this homography, so it's dt minus B over minus ct plus A. Y is not changing, and Y1, so this is the image of this is the image of this one. Y1 is sent to Y1 times 1 over minus ct plus A square, and Y2 is sent to Y2 times 1 over minus ct plus A square plus Y1 and times 2c over minus ct plus A third, the cube. You have the 4 component here. It is just writing that at the level of functions you are doing pre-composition or source composition by an homography here. And then here T is the inverse of Y. So source composition or pre-composition will be transformed in target composition, in the post-composition, and not by a matrix, but by its inverse. So here the group action is Y, T, T1, T2 is sent to Y, AT plus B over CT plus D, T1 times 1 over CT plus D square, and then it's a plus, it's minus T2 1 over CT plus D square plus T1 minus 2C over CT plus D third. And at this level, the action of the group is YU, let's say, is sent to Y U times as matrix product A, B, C, D. Okay, and I have to give, before I erase everything here, I have to give the way to go from this to this. I just described at the level of the solutions, but I have to be sure that we have a rational transformation or birational transformation from this manifold to this one that will send the path system here to this one, and then the leaves or the integral curves of this system to the integral curve of this one to the integral curve of this one, and I just have to give the polynomial formula to go from one side to the other side. So the formula are not very difficult. So here, to go from here to here, t is t, y is y, y1 is 1 over t1, and y2 is minus y t2 over t1 squared. And the other letter are the same. So if you do this transformation, you will map this system to this one, you will map this action, this group action to this one. On this side, the way to go from here to here, so y is always y, that's what the reason why I use the same letter, and then t1 is now u, I put 1 here, u1, 1 over u2, 1, t2, this is t, excuse me, t1 is 1 over u2, 1 square, and t2 is 2, erase this, t2 is 2 u2, 2 over u2, 1 third with a minus, I think. And this was so here again, if you take this equation here, so this 4 equation, you do this change of variable, you will obtain this equation here. If you look at the group action in the new variable t1, t2, and t, you will get this group action. And the only thing you have to be careful with is that if you try to inverse this formula, so if you try to write u1, 1 as a function of t, u1, 2 as a function of t, t1 and t2, etc., you'll see here that, for instance, this function, this coordinate is the square root of t1. Yeah, so you can choose two ways. Plus or minus the square root. If you choose one, you have another choice that is a minus. But if you write all the formula, you will see the square roots of t1 appearing in all the formula. As soon as you choose one, you have a well-defined map, and you remember what was written here, and that I erased, that for us, u is identified with minus u, because both matrix will, this matrix and its opposite matrix give you the same fraction here. So for this reason, if you have u or minus u, you have in fact the same element in PSL2, which correspond to this choice of the square roots. It's just the choice of a matrix that you use to give a matrix, a 2 by 2 matrix form to an element here. So it is not a problem, the square root. This square root is in fact well defined. Okay, so we start with this equation that looks nonlinear. We invert it, we decompose it in this way, and we had a linear equation. So now we have our problem here is to take one solution here and to evaluate in many convergent power series and see if we get some relation, algebraic relation between the function we obtain. And so we will translate on this side here. So maybe it is the last time we see this equation, and now from now on to the end of the lectures, we will only focus on this kind of equation, linear differential equation, or the one in fundamental form. Okay, so as I say, we will work on the linear model. And so I will say our goal in this framework here. So the weak Ax-Schanuel for J became the following. So you let U, small u, is a function defined, an holomorphic function defined on some disk or polydisk. In our case, it's a disk with value in PSL2 of C, holomorphic on a disk in Y, which is solution of our differential equation here. Okay. Meaning, if you compute D of U, you will have your matrix here. I will call it A times U. And A is this matrix. I will not write this matrix with all these entries anymore, so this is A, and it is a matrix that depends on Y. A is this one. Then you take some map, some functions. Let's say convergent power series in one variable S. And you assume something, so if the curve, which is analytic curve parameterized by S, is going to Y hat of S, and U evaluated in Y hat of S, 1, 2, 3. Yeah. This is a curve for any S. This is something in Y plus PSL2 of C to the N. The N coordinate in Y are this one. Okay. I do not put the index here, but it means all this one. And then this means the U evaluated in all this one, which gives you some 2 by 2 matrix. So if this curve has a small Zariski closure, Zariski closure is a set of solutions of all the polynomial equations that vanish on this curve. So small here means the dimension of, let's call this curve gamma, and I will call with the same letter the parameterization and the image of the parameterization, so the analytic curve. So this is also the image, and this will be the notation for the Zariski closure. If this is smaller than strictly smaller than 3n plus 1, then you will find two index between 1 and n, and you will find a variety in the product of the two here, an algebraic variety, such that the projection on the key L factor of your Zariski closure here is included in Y. So what means this? P, K, L is a projection of this product space to Y cross Y, just selecting the K and the L's factor in the product here. So this is exactly what you want, because this is just two copies of C. So this algebraic variety, if it is not everything, and it is not, okay, it is not empty, it is really something. This algebraic variety is given by the locus of a polynomial, yeah? And this projection means you are just looking at yk and yl, and they are in this locus of this polynomial. So this is a translation of what we want. We want to prove now that the game here is that now we are working with linear equation. Okay, so I will just So our goal is to adapt Ax proof. And for that we need nice equation. The question is this way to write the equation the good one? And the answer is no. So the good way to write the good equation are given by the coefficient of the following one form, that we call the principal form of the equation, principal one form, which is big omega. So you start with this. So you have this Pfaffian system here, minus AU. So on Y cross this. Okay. This is a matrix of one form in Y, and this BSL2 of Z will give you the coordinate here. You have to put in this matrix form. And then what you are doing is this, which is not natural from people from differential algebra, but it's very natural from the one from differential geometry. You're looking at this form here. So you see, so this omega, let's say on this, so this omega is really one form. And if you look carefully here, it takes value in SL2 of C, in the Lie algebra of this group here. It has, so this is the first nice property. The nice second property is that d omega is equal to minus omega, which omega. Yeah. And the third nice property is that the equations omega equals 0 has the same leaves, defines the same leaves, and we will write it a little bit upper. So the equations omega equals 0, so you have 3 one form as entries of this matrix, and now so that gives you a Pfaffian system here, and the equation here gives the same leaves or the same solution as your original equation, that was du minus au equals 0, as you just have multiplied here and here by u minus 1, which is an invertible matrix, so you just have taken linear combination of this form to get this form here, and I have nicer property than this form here, and what is very, very, very nice is this equation here. Okay? This one form, this set of one form here, satisfying that, will be the analog in this non-commutative situation of the closed one form we used in Ax proof. In Ax proof, remember that we have to use at some point that our leaves are in the kernel of closed one forms. Now we cannot have closed one form. Okay? It is related to the fact that the algebra is not commutative. And so we have to choose good form, and what I pretend is that this equation gives you good form, the analog of to be closed. And so we don't want to apply directly here, because what we want, if you look carefully here, that where is my space here? We are in a product situation. So the product situation means that we are in fact working with a block diagonal matrix, with the first block, which is the first 2 by 2 matrix, the second block is a second 2 by 2 matrix, the last block here, there are 2 by 2 matrix. Our equation is given by some A, which was this one, but A tilde is a product of, let's say, A of y1, meaning that you replace y by y1 in this formula. This is the first block. The second block is A of y2, and you go to the A of yn. So it is just looking at this omega tilde, which is I will write the fab system. Okay, this form is the best you can use to do the computation, but it is not the shortest you can use to write on the blackboard. So the shortest is surely this one, let's say. So now with this notation here and that, you get this fab system, which is just a copy of the same equation, this equation, this one, in different variable. So you use one variable, one independent variable for one equation, one independent variable for another one, etc. So, for instance, the leaves. So what I call the leaves are the graph of solutions, or it's not exactly graph of solution because it can be multi-valued. So leaves are of this system. Or, and I will call it with a tilde, they are just product okay. Each of these is living in this space with Li, which are leaves of the original equation. This equation here, omega equal to 0. Yes, it is just a way to write that to solve this equation. I can say it like that. If you want to solve this equation, you have to solve n equation independently, and then you take just the product of this equation, just putting the different solution u of u1 of y1, u2 of y2, u3 of y3, etc. in the same vector. That will give you something, in y cross p SL2 of c to the n. So we will use some nice property of this form omega. In the next lecture about a differential Galois theory, we will see why this property will give us some nice way to organize the computations. But I just want to end this part giving you some reason why we are doing this. So before looking really at what is a Galois group, etc., we want to give the origin of this form omega, which is here. So the origin is from a differential geometry. So start with a Lie group. Complex Lie group because we are doing everything over the field of complex. Yeah, so you have the identity here that I will call E, and the tangent of E is usually called the Lie algebra. It's Lie algebra. So we will define what is called the Maurer-Cartan, left invariant Maurer-Cartan form. Which is a form omega from the tangent of G, which take value in the Lie algebra of G, which is defined this way. You take a point G in G, a vector which is tangent at this point here, and you send it to the left by G minus 1, use the differential of this map, and you apply to V, where L G minus 1 is a map from G to G, which is called left translation by G, or G minus 1. Okay, this is our form, and it gives you some nice vector field here. So, if you start with V, in the Lie of G, okay, take a vector here, the pullback is a vector field. Omega minus 1 of V, that I will call V. There's an arrow here, it's a vector field on G. Okay, and you can compute this vector field in G, for G, a small point in the group. It is just the translation by G, maybe, of your V. The left translation here. So you see that it is a left invariant. Now what happens is that left invariant vector field are the infinitesimal generator of right invariant action. So this is an infinitesimal generator of right translation. So to see this, you just have to, so let phi be the flow of this vector field. Okay, the flow. V, which is defined somewhere, okay, somewhere in some open subspace, maybe not everywhere. And then you write that V is left invariant will give you that these commute with left action. It will give you that for any G in G, this will commute with the action on the left. And then you evaluate in the identity and you get that phi of G is G phi of E. So you see this is exactly the image of G is a right translation of G. So left invariant vector field generate the right translation. Okay? And so here are the main property of this form we are looking at. So this is a small lemma. Let H be let's say a subgroup of H, Lie subgroup G, and Q being the quotient map from the Lie algebra of G to the Lie algebra of G over the Lie algebra of H. Okay. The target is no more Lie algebra, it's just a vector space. And then you look at the Pfaff system, the equations, the differential equations. Q composed with omega equal to 0 on G. Okay, so this is a set of one form of G. You go from the TG to Lie algebra to this vector space. So you have, I don't know if this is dimension K, you have K different one form. And so you have integral leaves, so analytic submanifold whose tangents are exactly the kernel of this one. And this have as leaves the orbit of the right translation by H. So in this way, this form omega will give you exactly all the information you need about the right action of subgroup on the group G as soon as you know its Lie algebra. Okay? So what is the relation between this and what we are doing, you can do the computation when you have a group of matrix. So if you have G, which is inside GLN of C, then you can use matrix form. I will call this sending an element G to a matrix that depend on G. Then your Mower-Cartan form here is just looking at coordinate of vector and on the left multiplication by G minus 1. I will write omega is just U of G minus 1 D U of G. So using matrix notation, this form is just U minus 1 D, which is the first part that appears in our form big omega in the principal form. I remember that our form, try to write it d du minus u minus 1a u. And by choosing this set of equations, I choose the set of equations that is compatible with the right translation. So this form will give you the infinitesimal generator of the right translation. So this is the reason why we are doing that. If you choose, for instance, du minus 1 minus a, it will have something to do with left translation. But if you see your equation is not stable by left translation, or the set of solution of your equation is not stable by left translation, but by right. So this is this is the reason why, this theoretical reason why we have to choose this equation as good equation. So next lecture we will apply this to study the Galois group of a linear differential equation, and then we'll be able to state the main result in the fourth part and to apply it to Ax-Schanuel in the fifth part.